This is a lesson on rational functions and their graphs in a precalculus course. To review real quick, remember polynomial functions. We could write this in the polynomial form from a high degree to a low degree. And what I want to remind you and point out from that lesson was that polynomial functions include positive exponents only and are continuous and smooth. All right, when you look at the graph, they don't disconnect at any point, and there's no sharp corners or anything. When we move to rational functions, that's not going to be the case. They're not going to be continuous, and we'll call them a discontinuous function. And what you can see for simple rational functions, which is just a constant multiplied by 1 over a power of x, right? So simple negative exponents, a power of -1, -2, -50, -100. Any of those are a simple rational function. And when we look at those graphs, what you're going to see is what we call an asymptote. There are restricted values, and I had talked about this in the extraneous solutions lecture I put together. There are restricted solutions to this equation because there's an x in the denominator. We can't have that x equal to 0. That shows up on our graph. That should show up on your graph, and that will show up as an asymptote. That's what we're going to call an asymptote. So when I look at this, x cannot equal 0. That's going to be the y-axis here. So this is going to be the asymptote for this 1 over x rational function, just a simple rational function. So right away you're seeing how this is a discontinuous function. There's allowed values all the way up to x, that asymptote, and there's allowed values after that, but that asymptote is not allowed. That's not an allowed value, okay? So our graphs are a little bit different, and you'll see this for any form of a rational function. You're going to have some sort of asymptotes going on because you have a factor of x in the denominator. When we look at just general rational functions, and this is the general form of a rational function, what we're defining it as is a function that can be written as a quotient of two polynomial functions. So everything that you remember about polynomial functions on their own in regard to looking at that equation is going to be true, but now we're going to put one over another, okay? And because we have an expression of x in the denominator, we're going to have asymptotes, okay? And what I'm going to remind you just real quick is that polynomials, this is the general form of polynomials or the general form of rational functions. I'm going to be looking at the factored forms because factored forms are way more useful. I know books may introduce the general form as the end-all be-all, but when we're using forms of functions, you may have already remembered and seen with polynomials and quadratics that the factored form is much more useful. Much more useful. So let's take a look at the graphs of rational functions, what happens on graphs. So because these graphs are no longer smooth, I'm not going to categorize the behavior and point out different qualities of the behavior that I have before because it's a different type of graph, okay? The domain is dominated on what x cannot equal rather than what x can equal, okay? And that goes back to those asymptotes. We're definitely going to be interested in any zeros, any intercepts on here. You can see for the function that I have as an example here, there's a 0 on here. There's a y-intercept. It looks like this is 0, 2.5. So there are going to be zeros in different ways. If we have a shift up or down, we may have this function crossing the x-axis. You may be able to find x zeros, but we're still going to consider zeros. The other thing that we need to consider is vertical asymptotes and what we call holes. I'll talk about holes in a second. And it's because x cannot equal certain values because of the denominator, okay? When you look at this function over here, you can see that we have unallowed values at x equals -2 and x equals 1. Those are two vertical, what we call vertical asymptotes, okay? Vertical asymptotes. The end behavior as we go to the different ends in the domain for our function, that's going to be determined, that's our range, and y cannot equal certain values. depending on leading terms, right? When we look at the range in here, there's going to be an area in here where the function will never have a value. And that's kind of interesting. So horizontal asymptotes, you can see on here there's an horizontal asymptote. And y cannot equal certain values based on the leading terms of that denominator, or the numerator and the denominator. And I will talk about that in a few slides from now. But I wanted to highlight some of the important properties on a graph of rational function. Again, we have the zeros, we have horizontal asymptotes, and we have vertical asymptotes. Those are going to be important, the most important qualities that you want to look at when you're looking at a graph of a rational function. So let's explore these a little bit more. Vertical asymptotes depend on the factors of the denominator. So I pulled out the factored form here, and I don't know if you'll find this in any textbook, but this is the factored form. The asymptotes are going to be determined by what's going on in that denominator. That's the first thing I'm going to look at when I'm looking at this factored form. All of those factors down there can't equal 0, right? X minus v1 cannot equal 0, x minus v2 cannot equal 0, and so forth. So when I look at the graph over here, I can see that I have x equals -5 and x equals 1. So I know those terms down in that denominator must be x plus 5, maybe to a power, and x minus 1, maybe to a power, right? That's what I know. Looking at that graph, those vertical exponents come from the factors of that denominator. All right. When I look at the numerator here, these x1s and x2s, those are the x-intercepts. So this should feel familiar to you from polynomials, right? That's how we identified zeros on polynomials, is by looking at the factors of the polynomial. Simple, right? So when I look at this graph, let's see, that looks like that is -1/2 comma 0. So when I do an x-intercept, what I think is going to happen is something like this. That'll be a plus sign, right? -1/2, well, that's the x-intercept. So I know at least this much of the form of that rational equation is going on because of these vertical asymptotes, x-intercept. The one last thing I wanted to point out here is I'm noticing the horizontal asymptote. The horizontal asymptote is at 0. And what that tells me is that overall, when I simplify this as much as possible and x goes to positive or negative infinity, I'm going to get something that looks 1/x. And so that would give us an asymptote at x equals 0. Okay, so I'm going to go through this in a little bit more detail, but this is a highlight for you, what important things to look at on that graph. Vertical asymptotes are easy to find because they're right there, right? And they come from the denominator. While we're talking about the denominator, I need to bring up removable discontinuities, what we call removable discontinuities, but a lot of people affectionately just call them holes. You may remember from a prior lesson that I put together the idea of extraneous solutions. When I solve a rational equation, because there's factors of x down in that denominator, I have unallowable answers, right? And what we're going to call a removable discontinuity is when there's a common factor to the numerator and the denominator. So this might look like x plus 1 over x plus 1 times x minus 3. That's what I have here. Actually, I have a -3 here. So you see on this graph, there's a little hole. Do you see that? Holes are a single point where the graph is not defined, indicated by an open circle. So you can see that there's an open circle here at -3. So I'm going to guess, this is what I'm going to say, is that plus I'm going to have a common factor on the top and bottom, right? A common factor to the numerator and the denominator. That's what it's saying. That overall it factors out. This simplifies down to 1/x minus 3. But because the original function had those factors in there, that gets acknowledged onto the graph with a hole. Okay, my warning to you on this is when you're graphing equations, when you're graphing your rational functions, especially in Desmos, these holes will not come up accurately. They don't even come up at all, I think, in Desmos. So when you're looking at these equations, you need to make a mental note that there's this common factor on the top and bottom. And so I have a hole, I have that removable discontinuity that I need to make sure is on the graph that you properly submit to your homework or on an exam or homework or portfolio, what have you. All right. Notice that I was also able to identify the other factor down the denominator here because of the vertical asymptote. All right. Vertical asymptotes are always factors of the denominator. So that's a whole. Those are the restrictions on our x values determined by the denominator. The other thing that we need to consider is the other asymptote. These are vertical asymptotes or values that x can't equal. We can look at what values y can't equal. Okay, so that'll give us our horizontal asymptotes. And this, again, like I said, depends on reduced expressions when x goes to plus or minus infinity. So if I have 1 over x squared as x goes to positive and negative infinity, it goes to 0. That's approximately equal to 0. So we're looking at that end behavior, and I've divided this up into 3 cases. We're going to look at that leading term overall. When I simplify this down and I let x go to infinity, what happens is all of the lower powers of values in that equation, right? 2 and negative 5 are much smaller when x goes to infinity, so I wouldn't even worry about that. 4x over x squared plus 4x. And then when x goes really large, these two will cancel, and overall, like I said, you'll get an 1 over x squared. And that will lead to our asymptote when x goes to infinity, right? This simplifies down to y, and that simplifies basically down to 0. So we're going to have an asymptote at 0 because the function will go that direction, but it'll never actually reach that value, right? 1 over infinity is not actually equal to 0. It approaches 0. It goes to 0. So this function will never equal 0. The output will never equal 0, and that is why we get this asymptote at y equals 0. So that's the game we play when we're thinking about those leading terms. I'm going to take the leading term over the leading term and then simplify it and see what I get. So the first case we have is when the degree of the numerator is less than the degree of the denominator. We get 1 over x to a power, and you'll have an asymptote at y equals 0. Pretty easy. The next situation, I ordered these in sort of like normalcy. Like most of the time, you'll have asymptote at y equals 0. Most of the time. But it depends. The other situation that you might come across is when the degree of the numerator is equal to the degree of the denominator. All right, so let's play this game again. When x goes to plus or minus infinity, I'm going to look at the 2 leading terms. So the 2 leading terms here, and this is why we needed to talk about leading terms back in polynomials. Those are the 2 leading terms. So when x goes to plus or minus infinity, so let me write that down. X goes to plus or minus infinity. The function, right, plus or minus infinity, when I evaluate this at plus or minus infinity, we're going to get 3x squared over x squared, which actually simplifies down to 3, right? X squares cancel with x squared. I get 3, and you can see that on the graph. There's our horizontal asymptote at y equals 3, right? The function as x goes to positive infinity, negative positive infinity, it approaches 3, but it doesn't actually get to 3. It doesn't actually ever get to 3 because we can't actually evaluate infinity, okay? We can see when we have equal degree in the numerator and denominator, we're going to get y equals a constant, which is that leading term overall, the overall leading term value, all right, 3. The last case we have is when, well, we already did less than, and then we did equals, so you can guess that the last case is when it's greater than. The degree of the numerator is greater than the degree of the denominator. And this is the creepy case. I think this is the case where I'm not too worried if you don't understand this fully. I did make a note to say to you that, you know, I'm not going to assess particularly on this in detail. Not at a precalculus level. I encourage you to get Desmos or whatever graphing calculator you like to use out and play with it. Just put in different functions and see what's going on and what shape of the asymptote you get. But what we're going to do is play the same game again. We're going to let the function go to plus or minus infinity. We're going to look at those two leading terms. Same strategy, all right? Nothing different, but we're going to get a different result. 3x squared over x, which is a 3x, okay? So we're going to get a power of x up here. And what I'm going to tell you is that this results in a slant asymptote, especially if you have just like an x, a first power of x up here. That asymptote is going to be a line, and that's what we call a slant asymptote. I called it almost horizontal. It's not a horizontal asymptote, right? The other two examples we had were horizontal asymptotes. This is a slant asymptote, and that's why I said it's a little bit creepier than the other examples, and why I'm not going to test on it or assess on it in depth. It does involve synthetic division. The equation of this line is not just 3x. What I actually have to do is take x minus 1 and find out how it divides into 3x squared minus 2x plus 1. So you can do a long division there, or you can do a synthetic division where you can do your coefficients 3, -2, plus 1, and then go through and divide that and find the result. That result is the equation, that function, that f of x. I'm going to call this some function of x. All right, and that's what I'm saying up here. The slant asymptote, whatever is going on with that asymptote is going to be determined by that function that after you divide. It could be a squared function, it could be a cube function, it could be, right? Because the power of the numerator is bigger than the power of the denominator. So we're going to get a function of x, a polynomial out. This should be a polynomial. This is a line. It happens to be a line, and that's typically what you see in precalculus. It's just the easiest cases where the slant asymptote is just an equation of a line. If you include this in a portfolio, I think that would be an impressive thing, that you want to really, really understand the material and what's going on with asymptotes is each one of those examples. I put together a slide for how to sketch graphs of rational functions. I know this might be a moot point in our age of technology. You may have to at some point. Maybe you're on an exam and you need to just sketch the graph of the rational function. You can't look at a calculator. But what I do like this as a summary of all the things that I just went over. Given the equation of a rational function, we definitely want to get it in its factored form. Its factored form is going to be way more useful than any polynomial, general polynomial form. You'll solve for the y-intercept. That's an easy situation. When x equals 0, solve for the y-intercept, and I identify that on your graph. You should be able to identify that on your graph. Find x-intercepts. So that numerator, the numerator, we're going to set equal to 0. I mean, overall, you're setting the whole function to 0, but whatever's in the denominator, it cancels out anyway. So it's whatever factors of the numerator. And so you can see over here, there's no factors in the numerator. Right? There's no x-intercepts in here. Finally, we're going to find asymptotes. Because we have the factored form, we can go down here and find the vertical asymptotes. Those are going to be pretty easy. The horizontal asymptotes, remember we play this game, the function of plus or minus as x goes to infinity. And then we find out what that is, and then we're able to locate it on the graph. And then when you have all those parts together, you can sketch the graph. So I pulled up an example for us, and I pulled up a weird one because, doing an easy one, I think you may get the point. The easy ones are just, slow balls in here, but then they'll throw you a curveball, and I wanted to cover a curveball. This question asks, consider the function blah, blah, blah. What is the domain? What is the vertical asymptotes? Locate any holes, graph the function in any holes. Okay, so this is another situation where I'm going to tell you that you may actually just graph this in Desmos, right? But if you graph this in Desmos, it won't give you the correct answer because you may be seeing already that there's some common terms in the numerator. You see that common term in the numerator and the denominator? Both of these are common terms. And when I simplify this down, and this is what Desmos or graphing calculator would graph, is just this. That's what it would graph. It would not acknowledge this original function, which has limits on its domain. We know how to find limits on the domain. It says, what is the domain? We know how to do that. We're going to set each term as an inequality. Each term in the denominator is an inequality. X plus 1 cannot equal 0, and x minus 1 cannot equal 0. So that gives us our unallowed values for our function. X cannot equal -7, -1, and 1. So if I were to write out a domain, I'd go from -infinity to -7. I'd union it. I always put a parenthesis. I'd union it from there to there, and then I'd put another union from there to there, and then I'd put another union from 1 to positive infinity. So there's going to be 5 different regions of this graph, and because of these 3 unallowed values, right? We have unallowed values in here. When I look at what is the vertical asymptotes, that's defined purely by this simplified version. So our vertical asymptote is just going to be at -1. Okay, so when I draw my graph, I'm going to note that this is my vertical asymptote. That's the first thing I'm going to draw on my graph is x equals -1. I'm going to note that I'm going to have a hole, a removable discontinuity at x equals -7 and x equals +1. So that's our holes. C. Let's calculate them. F of -7, when I put in -7, I get 1 over -7 plus 1, which is 1 over -6. F of 1, that's where my other hole will be, is 1. F of 1 is 1 over 1 plus 1, which is 1/2. Okay, so those will be my 2 holes, -7, -1/6, and 1/2. That's how I solve for those holes algebraically. And then the last thing in here says graph the function in any hole. So when I look at this, I know I'm going to have an inverse function, and it's shifted left 1. Right? That's what it's going to look like. So let me get a different color up here. I'll get a green here. I could do a y-intercept. If I plug in f of 0, I get 1 over 0 plus 1, which is 1. So I know the point 0, 1 is on my graph. So 0, 1, there's that point 0, 1, my y-intercept. And then I am going to note that I have the last thing here, asymptote-wise, because this simplifies down as x goes to positive or negative infinity, I get a factor of 1 over x. So that means I'm going to have a horizontal asymptote at y equals 0. That's going to be our horizontal asymptote. I already put that up on the graph. Okay, so let's get my green out again, and I'm going to draw this function. So it's going to go up to infinity but never actually reach -1 as an x value. It goes smoothly through the y-intercept, not a corner, that's smooth, and then it'll head towards 0 at infinity but never get to 0. Okay, so there's that. I also know that there is going to be a symmetrical, it should be symmetrical, right? Around this vertical asymptote, it'll be symmetric about there. So I know that this is going to be a point on here as well. So again, 1 over x is a first and third quadrant. So I know that the negative value is going to go like this. It'll come from -1, go through that point, and then head off this way. And I'm going to put my 2 holes in here. Those are the last 2 things, right? Graph the function and any holes. So I put my 2 holes in here. So -7, I'm going to have a hole at -7, -1/6. And then I'm also going to have a hole at 1/2. Oh, I almost got it. 1/2. So that would be the graph. If you were forced to graph it without any calculator, that would be how you do it. By looking at that equation, you can find different points, different axes, different asymptotes, and also the holes in this specific case. if I were given the graph, I could be asked to write an equation for a rational function. So hopefully you've been noticing the things that you see in the function show up on the graph. So if I'm given a graph, I should be able to put that function together mathematically into a form, right? What we're going to do is assume a factored form. I think that's the easiest thing to do, is just assume a factored form, and then also let that leading coefficient be all the way out front. And so the top and bottom are just factored polynomials with no coefficients out front. We're going to have our x-intercepts. Our x-intercepts are determined up here, x1, x2, x all the way up to xn, however many you have. That's our x-intercepts. Our vertical asymptotes are determined by our denominator, so that's going to be v. Like I said, I don't think you'll see this version in any book. I like using v for vertical and x for x-intercept, but you may think about it in any way you like there, but that's the vertical asymptotes. That's how you would find those in the factored form. We're going to consider any removable discontinuities of any of these, like cancel for any reason, right? And the powers can be determined by local behavior, and we covered these in polynomial functions when we have multiplicities. So I put powers there, but I think it's multiplicities. So, you know, when you have a parabola as opposed to an x to the fourth and an x to the sixth, the power at that point is going to be determined by the shape of that function. And again, when you have like a cubic as opposed to like a fifth, gets wider as opposed to a line, the first power. So that this is a power 1, power 3, power 5. Power 2, power 4, power 6, right? That shape gets more extended as the powers, the multiplicities get higher. And then finally, use any other clear point on a graph to determine A. A lot of times this might be a y-intercept. I think y-intercepts are easy to find as long as you have a y-intercept. Any clear point, don't guess on points. So I pulled up an example here in order to apply these concepts. And you can see in the problem statement, it says write the rational function in proper notation for the graph showing the y-intercept, and they give us the clear point. I'm not going to guess what that is. They give it to me very clearly. And what I don't like about this graph is they don't have arrows here. I know we get a little lazy these days with our technology because it Desmos doesn't show arrows, right? Technically, graphs they extend that direction infinitely, and we assume an arrow on the end. So that should be what that looks like. Another point I'm going to notice on this graph is it seems like the function has an x-intercept. Oh, very interesting. So we have 0, 0.2, and then we have 1, 0. Those are 2 points on our graph here. So let's just start out with assuming our factored form. F of x equals a. I'm going to have an x minus 1 on top. I know there's going to be a minus 1 on top to some power. I don't know what that power is, but I'm going to let it be to a power. How do I know it's to a power? Actually, I think I might be able to figure it out. Notice that at this x-intercept, just like we did with polynomials, it doesn't pass through. And it doesn't pass through as a line, right? So it can't be a first power. If it passed through like as a line, it just went through, maybe it goes through curvy, right? That would mean it's an odd power, but because it touches the x-axis, I know this is going to be an even power, all right, for that. So I'm going to say even that, I'm going to guess that this power up here is a 2. I'm just going to let it be the easiest, simplest guess here is 2. And then when we solve for a, I think that'll take care of it. What goes in the denominator? I think another thing that we can easily fill out here is the denominator. You may be already thinking about it and filled it out in your head. We need the vertical asymptotes. We have a vertical asymptote at -1 and a vertical asymptote at 3. So I can go minus a -1 and then minus a 3. Those would be where our two asymptotes are. So that's the factors that go in the denominator there. Okay, so we have some pretty good stuff going on. I like this. What do I also notice? I think this is what makes students have trouble on this problem in particular, is that this is going on, and I didn't put it up here. Each one of these powers up in the denominator they can have their own powers. Each of these factors can have their own power. And how do I know what that power is? Well, I'm going to look at the shape of the graph again. Notice that these are both going in the same direction. I highlighted these parts around this vertical asymptote. They're going in the same direction, as opposed to around this vertical asymptote. Do you see that they're going in opposite directions? To me, that tells me that one's even and one's odd. We're going to need an odd power and an even power, and I need to figure out which one. Well, just like with multiplicities, if there's some sort of opposites going on, right? It starts and then it ends in the other direction. This is going to be an odd power, as opposed to when they're going in the same direction around that asymptote. On each side of that asymptote, it's going in the same direction as opposed to opposite directions. This is going to be an even power. So when I look at this, I'm going to assume that the x plus 1 has a power of 1, and I'm going to put a power of 2 at that x minus 3. Because I need an even power, I'm going to go with the lowest even power, the simplest one. I could put 100 up there. That would be an even power, but it's not the simplest. Always go with the simplest, lowest value that you can get away with there. Okay, so it looks like I have a pretty good form here, but I can't assume that a equals 1. I need to solve for a, and that's why they give me this y-intercept. I know that when I plug 0 in, right, when I find f of 0, I will get 0.02 out, or 1/5, right? So I'm going to set all of this equal. I'm going to plug in 0 where I see x in my function, that general form that I wrote out up there, to the first power x minus 3 squared. All right, negative 1 squared is 1. 1 to the first power is 1, and the negative 3 squared is 9. So I get a times 1/9. So I'm going to get a equals 1.8. That's how I would solve. I used a point, I plugged in 0, and I got out 0.2, and that let me solve for that unknown leading coefficient. So my function here is going to look like this. After all of that, all these things that you read off of that graph, finish writing so I'm not talking and writing at the same time. All of those things that you read off that graph, you can see come out, right? I think what happens here as x goes to plus or minus infinity, we're going to simplify this. What do we get? We get an x squared in the top and an x cubed in the denominator, which is 1 over x, which was my initial intuition, is that there's an asymptote here, but I kind of didn't want to say that because we can actually have y equals 0 there. So the ends are going to be determined by that asymptote, but not in that in-between region. So that's a little weird too. I think this is a more complicated function that you might approach. But so hopefully any other function that isn't as difficult, you see how to solve here. How can I figure out an even or odd function in the numerator? How can I figure out an even or odd or power in the denominator? How do I figure that a value out? Those are all the skills. Let's do another one just to confirm. Okay, just to confirm. What's going on in here? Write the rational function in proper notation for the graph. We're not given any point initially, but I am going to notice that, let's say, we have the y-intercept, don't we? I'm going to guess that to be 2.5. I'm not sure, but 2.5 seems fine. What do we have going on? Around the asymptotes, I have opposites going on up and down rather than going like this. So I'm going to write out my general form, my factored form, I guess. I know I have two asymptotes, so I'm going to have an x minus something and an x minus something in the denominator. And I was figuring out those powers around those asymptotes. I have two asymptotes, so that's why I have two factored terms in the denominator. And they are both look like odd powers. So I'll say that's an odd power and that's an odd power. I'm going to notice that I don't have any powers or any x-intercepts. You all see that? There's no x-intercepts. And here's the horizontal asymptote. I have a horizontal asymptote. So all those need to get worked into my function up here, how I write that function out. So let's keep working on the bottom. I have a -2 and a +1. Both of those I'm going to assume are to the first power, lowest power, unless it doesn't work out and I need to assume otherwise. So I'm going to let those be 1. What else do I notice going on? I notice the horizontal asymptote. I know horizontal asymptotes of the form y equals a arise when I have the power of the numerator is equal to the power of the denominator. So the power of the denominator equals the power of the numerator. That's when that happens. So what I will tell you that's going to tell me another thing about this equation, I have an x squared in the denominator. I know I have to have an x squared in the denominator because there's 2 vertical asymptotes. Has to be. So that means I know there's an x squared in the numerator. There has to be an x squared in the numerator. I also know that it can't have any like this going on because there's no x-intercept. Remember, if I had an x-intercept, let's say 5, right? That'd have to be equal to 0, and I'd have to see 5 as an x-intercept on that graph, but I don't see that. So that's why I know that there's just an x squared, all right, because of that horizontal asymptote, and there's no x-intercept, okay? I'm going to guess that the a in here, because there's a -2. Remember, as x goes to plus or minus infinity, this will be ax squared over x squared, which simplifies down to a. So I know a is -2. So there's one last thing that I wanted to add in here. I figured out a, I figured out the power of the numerator, I figured out the vertical asymptotes and the power of the denominator. The one last thing I want to add in here is there may be some sort of like vertical shift going on. I'm not sure, and it could get added as a plus c on the end. I like adding it as a plus c here, so that there's just something going on up top. And that would be fine with me, because if I did this equals 0, if I tried to solve for an x-intercept, I would get an imaginary answer, right? I can't have x squared equals some negative constant. So that would give me an imaginary answer, and that would stay consistent with what I see in the graph, that there's no x-intercepts, all right? So I'm going to use a point to solve for that c value, because I already know a. So what I note is the point I already solved for, 2.5 equals -2. I'm going to plug in 0 wherever I see x. 0 plus 2, 0 minus 1. Okay, so let's keep simplifying. 2.5 equals -2 times my constant over -2, which just gives me my constant. So there's my function. F of x equals -2 x squared plus 2.5 divided by x plus 2, x minus 1. At the beginning of this course, I bet looking at, if I told you you could look at this graph and write out the function for this graph, you would have never believed me. But what I'm doing is I'm training your eyes to look for certain qualities, certain points on that graph, and all of that stuff corresponds to something in that final function form. All of these numbers mean something on this graph, okay? The last thing I would do, honestly, to check my answer is I would put this guy into Desmos. I would just put it into Desmos, and then when I looked at the graph in Desmos, does it look exactly like this one? Do all the points correspond? Does it look and do exactly what this graph is doing, what I see in Desmos? And then that's how I would know I had the correct final form. The last thing I wanted to talk about in this lesson is inverse functions. We've covered inverse functions before. These should be pretty familiar to you at this point. An inverse function is for which the input of the original function becomes the output for the inverse function. And importantly for us, and we saw this maybe with polynomials, but more here, so I think with rational functions, is the domain of the function is the range of the inverse. So if we have the function and we have its inverse, all right, Whatever the domain is for the original function, that's going to be the range of the inverse, and whatever the range is for the original function, that's going to be the domain of the inverse, right? So what I typically do is, if I'm given a function, I will find its inverse, and then I will find the two domains, and once I know the two domains, that means I know the two ranges. I have an example of this in a second. Let's go over this a little bit more in detail. We have this addendum, and we've looked at this since the beginning of the quarter, that inverse functions must be one-to-one, and it must pass not only the horizontal line test, but also the vertical line test. And so you may see something that says limit to non-decreasing, like we have to limit to a certain portion of the graph so that our function is one-to-one only. Another sort of sub-skill, sub-learning objective, sub-task I have in there here for you all is admittedly making sure that you're sharp on your algebra. Execute algebra strategies proficiently and with accuracy. So you should have been improving in this as the Precalculus course goes along. I still see students struggle with this. You've seen me struggle with. Make sure you're paying attention to detail and going a little bit slow as you go through. Don't lose your factors, don't lose your negative signs, etc. Right? So let's do this example. I like this one. Given g of x, is this, simplify its inverse and determine the domain and range of each. Okay, so let me do this. Let's find and simplify its inverse. I know if I have just any function, in order to find its inverse, I'm going to flip the input and output. So that means wherever I see y, I'm going to put x, and wherever I see x, I'm going to put y. And so I'm going to do some algebra on this in order to solve this back again. I need y on one side and everything else on the other. So I'm going to do some algebra in order to simplify this. So I'm going to move this term over to this side and multiply it. That'll get rid of, if I multiply it on both sides, right? So I get 13xy plus x. Do you all see that? If I distribute, plus 11x, I guess. Plus 11x, right? So if I move this over here and I distribute my x to each term, I'm going to get this. Over on the other side, I'm still going to have 10y plus 2. I'm going to get my y terms together. I'm going to move this guy over here. I'm going to isolate the y's on one side and everything else on the other. So I get 13xy minus 10y equals, I'm going to leave that negative 11x out front, plus 2. Okay, so we still need to isolate y. Let's factor y out. 13x minus 10 equals negative 11x plus 2. So overall, my inverse function, I guess I'll write it like this. The inverse of g is going to be negative 11x plus 2 over 13x minus 10. I always order mine in powers of highest to least x, so that's why I write it out front, write it like this out up top there. Okay, so this is the fully simplified inverse. There's nothing more I can do on that one. You need to know when to stop with inverses. It says determine the domain and range on each. Well, remember on the previous slide, if I have f of x and f negative 1 of x, right, the domain of this one is going to be the range of this one. So if I figure out the domain here, I'll know the range here. Also, if I figure out the domain on the inverse function, then that will give me the range on the original function. So that's what I'm going to do, is I'm going to figure out the domain for each of those, and then that just by default means I know the range for the other one. Okay, so the original function, when I look at the original function, when I look here, all right, I'm going to have a limited value of x due to that. 13x plus 11 cannot equal 0, so x cannot equal negative 11 over 13. Doing algebra in my head. So when I look at the domain for the original function, I'm going to have from negative infinity all the way up to negative 11/13. And then I'm going to union that from negative 11/13 all the way up to positive infinity. I'm going to have a vertical asymptote right there at negative 11/13. And then I have a value for every other x. So that's the domain of g of x, which means that's the range of our inverse also. All right, done. The other thing I need to do is figure out, I can get a different color out here. I'm using more colors than I usually do. That's fine. For the inverse of the function, I cannot have 13x minus 10 equal to 0. So I know that x cannot equal 10/13. Okay, so that will give me my domain for my inverse. The domain is going to be negative infinity all the way up to that positive 10/13. And then I'm going to union it on the rest of the graph, 10/13 all the way up to positive infinity. So that was the domain of the inverse, which means it's also the range of the original function as well. Okay, so without doing any other extra math except finding the domains, I know the ranges. That's my pro tip for you. You can look at a graph on this one. I did not get the graph out on this one. I think if you're doing domains, and hopefully if you've learned well from me this quarter, if you're doing domains, make sure you know how to do all this algebra. You need to know how to do all this algebra, but I would look at the graph just to verify your solutions here. I'm confident. I didn't look at the graph. I know the answers too. Definitely look at the graph. Make sure that when you look at that graph, and you don't even have to do any algebra to look at the graph and enter a domain, but the algebra, like when you're doing this 10/13, negative 11/13, you can't just like look at a graph and get that point off, right? So you need to solve algebraically for those values, but check the graph and make sure that those verify and correspond.